thank you. And here I thought we were here to embarrass Alex with praise. Anyway, let's see if I can figure out how this works. Yep. I really had a hard time figuring out what to talk about to this audience. For starters, I didn't know who you were, how many of you there were, and there's an infinite number of things I could have talked to that relate somehow or other to Alex's work. But I decided others would probably talk more about Alex than I did, and I thought you'll probably be a bunch of technical guys, so I'm mostly going to talk about something that I'm excited about and that's fairly recent. I could, of course, claim that you should all know it by now, since you had time since, I think, September to hear about it, but my guess is that this will be new to some of it. I don't like litter. Garbage. So let's get rid of it. Anyway, it is about Alex here, and I'll get back to how this relates to Alex, but there's a very happy Alex. It's nice to see him when he is happy. He's just the Russian of the year in technology. It's a very great honor. And I fed him some nice bouillabaisse the next day. It was good. The day before, sorry. And that's a thoughtful Alex, which is, I think, more characteristic than the one I know better. That picture was taken quite a few years ago. I got in a new camera and I stuck it right up in his face. So that's the way I like to remember Alex. Yes, I know the first-rate rabble-rouser on technical topics. I know the really great Alex on form, but the thoughtful Alex is the one I like to remember best. And then, of course, Alex is not just a scientist. Those of you who have gone to his last class or been reading up on him could tell me what all of these things are and how they relate to Alex. But I decided I'm not going to tell you. You can figure it out. The slides will be available. And anyway, this is all something to do with Alex. It's all something that's important to Alex. And I chose the pictures so that they weren't too blatantly obvious in all cases. Anyway, so I'm going to talk about pointers. I'm going to talk about pointers. I'm going to talk about memory, raw memory, the stuff that you are at the bottom of all of your systems, not lambda calculus, just stuff down in the machine. And that's what a machine looks like to a programmer, right? There's a bunch of objects sitting in memory, and you can get to them somehow. There's the pointer. And that's the list. And everything else roughly is built on top of this. And you will notice that, well, that's roughly C, right? And together we have got roughly the STL. And basically, you can build lots of good things about it. Now, I'll say a little bit about why I like pointers, but the problem is that they're not respectable. They're sort of not allowed into fine rooms. They're dangerous, low level. They're not part of math, people tell me. And there's a huge ABP crowd, anything but pointers. And so since this is so fundamental to what we are doing with C++ and with some of Alex's work, I think I'm going to go down to the real bottom at the thing and talk about that. And by the way, try and make this respectable. And so I start at the bottom, and Paul will take you to the high level towards the end. It's not all going to be bit fiddling here. And actually, I won't get to the bits. I'll get to the bytes, but that's it. Okay, so I like pointers. I mean, they are what there is in the hardware. So if you want to use the hardware, you have to do pointers. That's how you address things. They're machine addresses in sweet and sour sauce or something, but when you do them right, they're machine addresses. And there are good reasons why they're popular and useful. They're simple. There's nothing simpler you can do to address something in memory. They're general. You can do anything. Obviously, you can do anything because anything on the machine is built on top of it. And they are fast. Nothing on a machine beats the machine's addressing mechanisms, right? It's obvious. And they're compact. If you want to address something, there's nothing better than an address. Anything else, you add bits and bytes and stuff to the side to make them complicated. They're supposed to do good things for you, but they aren't as fast as a basic pointer. So if you can get away with a basic pointer, you win. So the C memory model has actually served us very well. It's old. I mean, Dennis did it in '72. That's a long time ago. A lot of us weren't there. And it basically is the foundation of a lot of things. So I think we're spending too much time trying to get away from this stuff. It's useful. So there are, of course, problems. And I'm going to go through the problems in case some of you don't remember how they burnt you. And then, having characterized the problem, I am going to try and show a solution. And since we have executives here, there's an executive summary here. That's the shortest one. But anyway, we will offer complete type and resource safety in C++. We will have tools that guarantee it, and we will have no litter, no resource leaks for whatever definition of resource, no garbage collector, because if you don't generate any garbage, why would you need to collect it? And no runtimes overhead. I mean, we can do these things if we slow down the machine and go away from the machine. But let's keep the speed up. I want to simplify the code. And this is part of a more ambitious project known as the C++ Core Guidelines that I gave a keynote at CPPCon this year about that project, with this talk as roughly a subset. But that's where it is. You can go it. It's available. It's being used in quite a few places. If you don't like it, wonderful. You can make a pull request, or you can send me an email. We're fixing it. It's totally out in the open, and we're working on it. And so what we want is C++ on steroids. A lot of people say they want something better than C++, and they want some neutered version of it, where you can't harm yourself. I really want more of the good stuff, not restrictions. And so let's just look at the problems a bit. Lifetime can be quite messy. So if you have an object and you have some pointers to it, you'd like to know when you can safely remove the object. And if there's only one pointer to it, well, then a garbage collector can do a good job. But you know, sometimes there's many objects, and now you have many pointers, and you have to count them. There can be cycles for extra fun. And then you have things that you don't have a pointer to. Maybe you wrote it out on disk and are going to take it back tomorrow, or something like that. This makes it difficult. And then, of course, you have pointers that doesn't point to anything. Just this is not an easy problem. There's a reason why a lot of people don't like pointers. They can be dangerous to your mental health. And furthermore, in C and C++, there's things like you can have pointers to something that's statically allocated. You can have something on the stack, something on a heap, and something hidden inside another object. And if you take, say, a linked list and link it through all of these things, you're basically hosed. Because a pointer does not tell you what kind of memory it is pointing to. It just tells you what the type of the thing is so that you can read and write it. Some of these have to be managed, have to be deleted, and some of them, well, if you do it, you crash. So this is not that easy. And finally, there is resource management here, because some of the things we really mustn't lose aren't just memory. So if we just do memory management, again, we die. We run out of file handles, we run out of thread handles, we can have map keys. That one is really hard to solve. But basically, some of the things we want to deal with under the label of resource, they're in objects, but they're not pointers, so just dealing with the pointers is not enough. So, and then pointers are good for access, but it can be somewhat messy. So there's a pointer to a bunch of elements, a pointer to a single element, a pointer that unfortunately went beyond the end of an element, and so you can get range errors, and well, that one went up there somewhere, stray pointers. And then you have constant and zero pointers and other stuff. So we would like to not having any litter, not having any leaks, no corruption of memory through pointers. That's what we'd like to. We would like to guarantee it. And there's a few things we have to make sure to this. And then we have to make sure that any fully constructed object is destroyed properly. That's the way we take care of the non-memory resources. And that's fairly easy for things that are on the stack or on the on main memory. But if you put them in free store and just have a pointer to them, then it's easy to lose them. So to handle this, you have to deal with pointers. And there's lots of partial solutions. I mean, you can ban them and see what else you do. You have to do very difficult, complicated things that in the end gets expensive. You can have manual memory management, which is a right royal pain, sometimes work, but you end up with problems. Garbage collectors, they're expensive, use a lot of memory, use a lot of electricity, and you still have to deal with resources by themselves. Static analysis, I mean, just take a program, analyze it, and keep analyzing it till you're proven that every object is deallocated, no pointer is doing wrong. There's a couple of things wrong with this. First, that you can do it for tiny little things if they're not too complicated, and you can't do them for real programs. And we can usually defeat it anyway because static information is imperfect. Smart pointers, you can litter your program with smart pointers. Counted pointers is old-fashioned garbage collection. You can have unique pointers for optimization. You can do all kinds of things here. Again, I think, functional programming, you just eliminate all the pointers and you get a different kind of programming. Again, it has some problems with dealing with the hardware. My observation here is that if you start down any of those tracks, you end up you have one tool, one hammer, and everything looks like a nail, and you can end up with quite complicated stuff. So we have old problems and old solutions. This is to remind you what the world looked like a long, long time ago, and we have known these problems, we have tried to solve them ever since computers looked like that. And of course, this is only a small part of the computer because a real computer in those days did not fit on slide. And so manual resource management doesn't scale. Smart pointers add complexity of cost. I was looking at it, there's these shared pointers, counted pointers, and what does a count do? 0 to 1, 1 to 2, 2 to 1, 1 to 0. That's about as much that count has ever done, because you just took something here and moved it over here, and the use count went berserk. The use count has to be protected under some kind of locking mechanism. Lock-free is also a locking mechanism. And so there's a cost involved, a complexity. And if you get smart pointers, you get 1, and soon you have 10. And now you can't figure out what you're doing. Garbage collection is a partial solution, neither ideal nor complete. And static analysis doesn't scale. So let's see what we can do. The solution that I'm going to present here is, first you want to be precise about ownership. You want to know an owner is something, is a pointer that you must delete when it goes away. And non-owners are things you mustn't delete through. And we want to statically guarantee this. Then we want to make resource management implicit, RAII. Basically, we grab resources explicitly, usually, sometimes indirectly, and we do not want to explicitly give them back again because we forget. We want to eliminate dangling pointers, that's essential. And if you want to avoid null pointer problems and range problems, you actually need some runtime checking because there is no information available at compile time to tell you what you're doing. That there are other problems with pointers, but they are dealt with traditional techniques. Think casts and unions. We'll get to that, but that can be done. So basically, there's a constraint on the solution. I'm not about to retire right now, but I would like to see the solution now. I don't want to sit down, wait for somebody to design a new language or design a new language, wait 10, 15 years till it can be used at scale. No, I want it now. I don't want to wait for a new standard. I don't want to spend all my time arguing with the standards committee about it, and I want it to guaranteed. Just be careful. It doesn't work too well and it's fairly unpleasant. And we don't want to sacrifice the good things that we have about C++ here, generality, performance, simplicity, portability. I mention this because, again, if you narrow the domain sufficiently, you can solve just about any problem. But that's not what a general purpose programming language is for. So let's look at the resource leaks. Just do RAII, root every object in a scope so that the destructor takes care of it. And that's what all of these things work in. You can now get no naked new, no naked delete. And basically, it's been there since '79, and it's still, I think, the best way of dealing with things, the simplest way. There's no memory that's better than the stack. There's no resource management that is better than simple pairing of construction, destruction. Yeah, but everything else comes down to having to defeat that one. That's my nightmare. Dangling pointers. So here we have an innocent-looking little function. It gets a pointer in and it deletes it. Sure, here's an innocent little function. It makes an object. It calls f, and it does a lot more. And finally, it uses q, the pointer it took away there. And you can see the problem here. I mean, how do I know this one could be deleted? Well, it can. It came from a new, but you know, I used the pointer after it's gone away. And bury this code in 100,000 lines of code, and it gets hard to find. And it gets hard to run analysis on it to find it. Even computers are not good at finding this kind of stuff in large scales. And then people start with other techniques, like the smart pointers or the garbage collector. Okay, but we must handle this. I mean, this is the crucial thing. We must. If we don't eliminate dangling pointers, we can't have type safety. After all, I have a pointer. One of your objects come here next hour. I write to it, and you don't have that object anymore. I have violated the type system and scrambled your object. You wouldn't like that. Memory safety is compromised. It gets hard to guarantee everything is returned without a garbage collector. And of course, resource safety, because resource is an object. And what we're trying to do is to handle this by a combination of rules. That is, we want to know what is an owner. We assume ordinary pointers are non-owners. So what I'm up to here is I'm going to make a good old pointer, int star, respectable, because it'll be safe. No layer of stuff on top of the machine. And what we do is simply catch all attempts for a pointer to escape into a scope that is enclosing its owner. So, and then, by the way, there's many ways of escaping. If I have a pointer and I want to put it in a place where I can create trouble later, I mean, I can throw it, I can return it, I can have a reference parameter, I can have stick it in a container that lives for a long time, bind it in a capture from a lambda and such. So what I'm saying here is the idea. The engineering is here. There's currently a 50-page document explaining all the details here, and we're still working on it, finding one or two. But this is not science fiction. I am a little bit pissed with my friends at Microsoft because they are going to deliver this month or the next instead of the previous month, the first static analysis of this, but just a little bit pissed because I am so happy we can do this stuff. This is real. I think at the end of the year, we will start seeing in real code bases this stuff being deployed and this kind of monster disappearing. Let's see. Anything that holds an owner is an owner. Fine. So basically what we need to make sure of is that all our pointers to our object is above in the call stack. Assume the call stack grows upwards, not down, but anyway. It mustn't get down there. If we can guarantee that, we have done most of it. And so we can look at this and run an analysis on it. I'm deleting a non-owner. I just violated the rule, right? It's easy to check. I have a new here. There's two things wrong here. First, I'm assigning an owner. Obviously, that's an owner coming out of new. Also, I have just violated exception safety, which turns out to be roughly the same thing. So that one will be caught too. Dead easy. I call f of q not a problem, but we will never get there. We can't get past this point. And this is local analysis, so it's very easy. So anyway, you represent ownership. First of all, give people an ownership abstraction. Use vectors, smart pointers if you have. Low level, we mark them as owners, and I talk about pointers, but I mean anything that points to something. So if you have an offset that you add to a pointer, that's a pointer. If you have a reference, it's a pointer. Fine. And we mark it as an owner. The initial idea was yet another kind of smart pointer. You have an ownership pointer. You have a bit in it. But everything's wrong with that. I have to do bit manipulation to read that bit. It's not ABI compatible, so you can't use it in your old code. And anyway, it's not C compatible. And it's slow, it's complicated. And now we get yet another smart pointer. Ownership pointers, counted point. No, we don't want to go there. So that's the guideline support library. It's just a handle for static analysis. And we use it for things like inside the ownership abstractions. Here we have a standard kind of vector. It has 3 pointers. One of them says that this is my memory, and the other 2 says where things are in the memory. And so we can now, in a safe way, write our standard abstractions. And they don't cost anything. The other place where we use it is where we have an API that we can't modify. It takes pointers, so we will slap an owner on it. And if we now have an owner P, and we can transfer the ownership, see, it went there. We can try a non-owner and make it into an owner. No, you can't, because it isn't an owner. We can delete an owner. Yeah, we are supposed to delete an owner. If I forgot this one, this function will not pass. And we cannot delete a non-owner. Again, all local analysis easily done. You can have the compiler do it. Currently, it's being done with tools. Microsoft is doing it, and there's some startup work at Google on this too at the Clang. Okay, so basically owner is a low-level mechanism. If you've ever tried to annotate, again, 100,000 million lines of code, if you are trying to do this, sooner or later you just become the problem by putting owner on the wrong thing. So just using this, which looks attractive to people thinking about this much code, no, put it inside the ownership abstractions more often. And basically, it's sort of a mixture. I was thinking of these medical cocktails people get against bad bugs that can survive any of these approaches. We'll give it a dose of library, type system, static analysis, RAII, and we get it. Avoid dangling pointers. You mustn't mix owners and non-owners, because then you get into trouble. You must also know what it points to. So there's an owner. Okay, you can't return that because it says it returns a non-owner. You also have to know that you mustn't return a local pointer. That has been stopped all the time. But if I got something in, I can also pass it out again. You will realize this is what makes the STL work. You can pass into a normal function, run it at max speed, get it out again. There's no memory management involved. So we've separated all the things that work with, say, iterators from the ownership stuff, which is at a different level. And you can try and do that. Here's another version of that. I am putting into a vector a pointer I got in, so it may not be an owner, but it's not an owner here. And a local and something that is an owner, we cannot allow that. If you want to write abstractions and mix things up like this, you have to do trickery with bits that tells you what this means. So 1, don't do it. 2, if you do it, suppress the analysis and fiddle with your bits yourself. You can do it. So basically, there's a summary. Never let a pointer point to an out-of-scope object. And it's not just pointers any way you're doing it. We're still working on concurrency. Basically, keep your threads alive. Then you just have 2 stacks, and you can treat the other object stack, the other thread, as just an object that could outlive what you're having, so you can do it. That needs more work. I said the core guidelines are not finished. We can use all the help we can get, but we're doing it, getting more and more of the bugs out of the stuff. There are other problems. There's other monsters lurking here. Range errors, we have library for that. Null pointers, we have library facilities for that. You can overuse smart pointers to the point where they become a problem. All of these single solutions to the problem eventually become the problem. And there's other ways you can break the type system. Instead of unions, try user variant, cast. Try not to use them. You don't need them as much anymore. And basically, just test everything. It's too expensive. It's not hygienic. And so basically, with RAII, no dangling pointers, we can get no leaks. We can eliminate range errors if you are willing to pay for a few tests. Remember, formalizing the tests allows the compiler to eliminate a lot of them. That's important. You can't just test everywhere. And eliminate null pointer dereferences. And then after that, we'd like to go after the logic errors. But here we go after one particular kind of error, making pointers actually work. And there's more information. There's a paper that I mainly wrote, which explains this in about 20 pages. There's 2 ways of getting it. You can go to the GitHub where you find the whole thing, and you will find all of this. You can go to my homepage and go to publication. You'll find this paper. That's how I suggest you start with the explanation. That is the last time I looked 50-page explanation of how you do basically the symbolic computation to do the leak analysis for individual functions. And here is the theoretical paper from Pobble about why the resource model is safe. That's where the code is. See, this is the problem. It does not say last December, but they promised me it's coming real soon now. And there's some videos from CPPCon that's related to the general project. And so I think where this fits in is that I think we all like the STL. And when it came along in the 90s, it was the biggest difference between old C++ and the C++, the standard in 98. And you could conjecture that C++ wouldn't have existed if it wasn't for the STL, because they would have been overwhelmed of other novelties. But it did leave the problem behind that C++, modern C++, is littered with pointers, sometimes called iterators, and they have the model of accessing things that's allocated elsewhere and all that kind of good stuff. I think this one actually backs it up and makes it safe. That's basically what I had to say for now. Boat is a surprise. You're not an O'Brien fan? No, it's fairly new. But basically I'm expecting rough weather, and this boat here happens to be a very fast boat, rather good in rough weather. I know there's other O'Brien fans in the audience. It's a story from the Napoleonic Wars. It's very good airplane reading. Anyway, yeah, don't expect this to be totally smooth. Is there questions? Or do we have time for questions? No questions. Okay, so what was it you just... Sorry. Thank you. Special rules for Alex.